All through Calculus 1, we deal with derivatives. We deal with a function, let's say f of x equals 8x cubed, and you take the derivative. Right? And we learned lots of different ways of taking derivatives for different types of functions. Right? This one's just polynomial, so I'm just using the power rule here to take the derivative of that function. Right? And then we would use the derivative to do many things. Now, in Calc 2, we're going to be going the other way. Suppose I told you, suppose we knew that the derivative of the function was 24x squared, and we didn't have the top part there to look at. So I said I didn't have that first part available to you. You're only looking at this, and I say, all right, well, if that's the derivative, well, what's the function? Right? And so we're going to have to look at lots of different techniques of how do you work derivatives backwards. I mean, you just figured out how to do them forward. Now we're going to go backwards. Well, with polynomials, you're looking at something like, the derivative of x to the n. If I take the derivative, it's nx to the n minus 1. So it's like, well, taking the derivative, the power always goes down by 1. So taking an antiderivative, maybe the power should go up by 1, right? And the coefficient out in front is the power that came down. So there's an extra. When I take this derivative, a 3 is going to pop out in front. So the 24 must have a factor of 3 in it somewhere. So what's 24? 8 times 3? Yeah. So if I just take that 24 and divide it by 3, then this should be 8x cubed. All right. Now, that's all fine and dandy, but there's someone else that might say, you know what, wait a minute, I think that this function here, g of x equals 8x cubed plus 2 is an antiderivative of that thing. I haven't really defined the word antiderivative yet, but that this function has a derivative that's equal to that. Both of them do. It's true. So then there's the question of what other functions are there whose derivative is equal to this one? Well, it turns out, because of the mean value theorem and the constant difference theorem, if you got two functions with the same derivative, then they must differ only by a constant, right? So all of them, let's write this as capital F here. If I wrote 8x cubed plus c, and where our c is just some unknown constant, then this should be describing all of the functions that when you take the derivative, you end up with this 24x squared. Okay? So this is what we call an antiderivative. And let's make a definition here. Definition. Capital F of x is an antiderivative of little f of x if the derivative, what just happened there, of capital F of x is little f of x. Now I don't say the antiderivative, I use an indefinite article here because there's not necessarily one. In fact, there will always be infinitely many, because as soon as you find one, you can add a constant to it, and you've got another one. So this is called an antiderivative. We also have the notion of what's called the general antiderivative, and that is this thing right here. Definition. Actually, let's write it this way. If capital F of x is any antiderivative well, it looks ugly, doesn't it? Antiderivative of little f of x, then the expression f of x plus c is the general antiderivative. A particular antiderivative is a function. The general antiderivative is a family of functions because you're taking all the different possible values of c. And for the time being, we're dealing with functions of real numbers and real outputs. So c is any real number here. So infinitely many. What we now need to do is to be able to look at functions that we took derivatives of and turn them around into antiderivatives. Right? We already looked at that, the notion here of the polynomial, where this is the derivative rule. Let's write this as an antiderivative rule now. So if I have, f prime of x equals x to the n, what's f of x? Well, the power needs to go up by 1, and I need to divide by, I think, the new power. That is, the antiderivative is the exactly reverse process of derivative. To take the derivative, I would put the exponent in front, and then, so I'd multiply by the exponent, and then I'd drop the exponent by 1. The reverse of that, so doing the opposite things in the opposite order. So rather than multiplying by the exponent and adding 1 to the exponent, and subtracting 1 from the exponent, multiplying and subtracting, I'm going to add 1 to the exponent and divide by the new exponent. Notice that when I take the derivative of this thing, the 1 over n plus 1, well, that's just a constant that comes along for the ride, and the n plus 1 would be multiplied out in front, canceling the other n plus 1. There's just a 1 out in front, so you want it to cancel. And then you drop that down by 1 from n plus 1 down to n. So this indeed is an antiderivative of that. To get all the antiderivatives, I better add the plus c, right? So this is now the general antiderivative of x to the n. It's the power rule for in reverse. Lots of different functions that you knew how to take the derivative of. We knew how to take the derivative of sine x, right? So the derivative of sine x was cosine x, which tells me that going the other way, if f prime of x equals cosine x, then an antiderivative would be sine x, and the general antiderivative would be sine x plus a constant. So on page 345 in your textbook, there's a table there in the middle with a bunch of different functions where they're functions that we knew how to take the derivative of, and so now we know how to take the antiderivative of. One of the ones that I think is a little less obvious, I know that I had trouble with this when I was in this class as a student. They're just the functions that look different than their derivatives. Remember that the derivative of natural log x is 1 over x, which tells me that if I've got 1 over x as the derivative and you're asking me what the function is, well, it's going to be the natural log of x plus a constant. Actually, if you look at the textbook, they throw an absolute value sign in here. I'm going to save that discussion for another video, but really what it boils down to is that 1 over x is defined for x is positive or negative, not 0. But natural log of x is only defined for positive x's. And it turns out, because of the symmetry of this function, slapping an absolute value in there will make that work. I'll discuss that in another video. But this one is one where it is an x to the minus 1 power, and you might be tempted to take an antiderivative using this thing right here, where you increase the power by 1 and then divide by the new power. But hopefully you'd be tipped off, because if you take this negative 1, can I get these both on at the same time? If you take this negative 1 and increase it by 1, that's going to be x to the 0 power, and then you got to divide by 0? Something's wrong. So this power rule up here, this power, I point with my finger, and I realize you can't see me point with my finger, but I think you can see when I do this. This power rule is only going to work when n, come on now, why is this not writing? Just a minute here, let me grab my pencil again. There we go. This is going to work when n is not equal to -1. Right? If n is equal to -1, then you're looking at the derivative of the natural log, so the antiderivative of x to the -1 is the natural log of x plus a constant. Yeah, that's the value. Again, I'll explain in the next video. Yeah, one more that I want to do that I think is less than obvious, and that is, back from calculus, we did some work with inverse functions, in particular inverse trig functions. And so the derivative of the inverse tangent function of x was equal to 1 over 1 plus x squared. This, to me, just, I remember learning it thinking, dang, they want me to just remember that? I have ways of now figuring it out, and so this isn't quite so mysterious. But still, if I know this derivative, then going backwards tells me that if f prime of x is equal to 1 over 1 plus x squared, then, well, then it means f of x is equal to the arctan, or the inverse tangent, right, plus a constant. I felt like when I was taking Calc 2 that they want, oh, you just got to remember this. You know, when you see this, it's going to be that. Well, it certainly is a quick way of doing it. We'll have a technique later on this quarter which works for a lot of different things, particularly when you've got you know, either a sum of two squares or a difference of two squares. Here's a 1 is a perfect square and x squared is a perfect square. So I got a sum of two squares. There's these things called trig substitutions that'll work in a wide variety of situations, including this one. So if you can't remember this antiderivative, then we're going to have other ways to be able to figure it out. And this is one thing I didn't understand as a student, that there are other ways. It's not just, oh, memorize each one. Right? We have different ways of understanding it. Anyway, you're going to be asked to just take a bunch of antiderivatives in the homework, and we're going to have to look at some of the little variations, at least on an introductory scale, over the next day. But I think I'm going to stop this video right here, and we'll do some examples in the next video.